Modern graph representation learning relies on a foundational operator, the Graph Laplacian. It dictates exactly how signals propagate and smooth out across a network. This operator functions on a strict rule known as the Homophily Assumption. It mathematically penalizes any variation between neighboring nodes, forcing adjacent data points toward exact scalar equality. In complex systems like knowledge graphs or heterophilous networks, adjacent entities are systematically different. They relate through highly specific contextual rules rather than simple similarity. Applying the standard Laplacian to these complex networks triggers a catastrophic engineering failure in deep learning known as oversmoothing. As feature diffusion runs through deep neural layers, heterogeneous note signals are washed out entirely. Solving this requires an architecture that evaluates relational consistency instead of enforcing basic scalar agreement. Oversmoothing is the inevitable physical consequence of applying a homophily-based mathematical operator to deeply relational data. We need a new geometric framework, one capable of natively encoding context-dependent agreement directly into the structure of the network. The solution emerges from the local to global mechanics of algebraic topology. It is called the cellular sheaf. At its core, a cellular sheaf is a discrete data structure. It assigns specific algebraic spaces and exact transformation rules to the individual cells, the nodes and edges of a network. A cellular sheaf defines precise translation rules governing information flow across every edge in the system. This structural upgrade enables network analysis to model deep, relation-specific geometry. The standard Graph Laplacian dates back to the mid-19th century, originating in Gustav Kirchhoff's analysis of electrical networks. This diagram shows the incidence operator across a single edge. The formula calculates the exact difference in state, scaled by edge weight. Multiplying by its adjoint yields the Laplacian matrix. This generates the quadratic energy form, an explicit penalty on local variation. Because of this penalty, the kernel of L, the state where the network reaches absolute zero energy, is populated exclusively by globally constant functions. The architectural DNA of the classic Laplacian is built to optimize for a universe where every connected entity is mathematically identical. To build the physical geometry of a cellular sheaf from first principles, we must start at the nodes. Instead of a simple scalar value, we attach a localized vector space, a stalk, to each vertex. The connecting edge carries its own shared stalk, where data is compared. We use linear restriction maps to project individual node data directly into this shared edge space. These restriction maps can execute complex operations, shifting coordinate systems, applying orthogonal rotations, or filtering out partial dimensional observations. By combining individualized stalks with customized restriction maps, the network acquires the mathematical vocabulary to compare different data structures in a shared abstract space. The degree zero sheaf coboundary calculates the exact mathematical difference between states projected into the edge space. Multiplying this by its adjoint produces the Sheaf Laplacian. Its quadratic form explicitly penalizes the failure of local consistency rather than mere variation. If an assignment of data across the network perfectly satisfies every restriction map simultaneously, the energy drops to zero. That state is a global section. This space of perfect, globally consistent states populates the kernel of the Sheaf Laplacian, known algebraically as H0. In a Sheaf Laplacian, signal smoothness requires perfect frictionless alignment with the network's relational rules, rather than uniform identity across nodes. We translate this spatial geometry into a block operator matrix. The diagonal blocks compute local self-comparison for each node. The off-diagonal blocks represent the negative comparison operator, coupled precisely through mappings into the shared edge stalk. This maintains strict backward compatibility. Restricting stalks to one dimension and simplifying maps to scalar weights collapses this entire matrix into the ordinary Graph Laplacian. We plug this matrix into the continuous sheaf heat equation. The derivative of state x equals negative LF times x, which drives feature diffusion. Standard diffusion washes features out to a flat constant. Sheaf diffusion mathematically drives node states strictly toward the complex high-dimensional space of global sections. The visual outcome is consistency-seeking smoothing. Neural sheaf diffusion cures oversmoothing, allowing neighboring nodes to hold entirely different raw vectors while maintaining absolute relational equilibrium. Grounded in applied topology, the Sheaf Laplacian scales to higher dimensional geometries like simplicial complexes. The degree K sheaf coboundary operator measures consistency across faces and higher cells. This yields the discrete sheaf Hodge Laplacian formula, summing the degree K coboundary and its adjoint with the degree K-1 terms. States falling perfectly into the kernel of this higher-order operator are known as harmonic sheaf cochains. These harmonic spaces mathematically represent sheaf cohomology. They act as precise analytic detectors for topological obstructions that prevent global consistency. The Sheaf Laplacian provides a rigorous analytic bridge connecting discrete data structures to continuous topological geometry. Machine learning's contemporary frontier focuses heavily on the inverse problem, identifying the correct cellular sheaf directly from data. Rather than manually prescribing these structures, engineers face the immense computational challenge of learning optimal restriction maps dynamically from raw node data. A major roadblock is gauge symmetry. The optimization space is flooded with redundant coordinate transformations, forcing algorithms to learn how to ignore these artifacts to find the true underlying geometry. Cutting-edge research pushes past this using Bayesian parameterizations and Pak-Bayes spectral bounds and directional sheaf networks to stabilize the learning process. To accurately analyze complex data, the field must move beyond the Homophily Assumption in standard Laplacians. Replacing scalar equality with relational geometry provides a mathematical foundation for architectures that natively encode the structural complexities found in real-world data.